In this video, we're going to look at how we find equilibrium concentrations of our reactants in our products if we're given a K. And this is a simple process. It just takes some practice to get down. And there's some steps we can follow. So the first step, make your ice table. Second step, calculate your Q. Determine if Q is smaller than K or bigger than K to know if we're going to make products or if we're going to make reactants. Step 3, do the C column in your ice table, your change, to know if you're going to lose X, create X, and what your coefficient of X will be. Step 4 is solve for X. And there's two different ways we're going to look at solving for X. The first would be a second order quadratic formula. And the second way is through the approximation method. And we're going to look at examples for both of these. So the easiest way to learn this is actually look at examples. So let's go through this example together. So we have a reaction here, HC2H3O2 plus water goes to hydronium plus C2H3O2 minus. We're given a Kc. And then we say initially we have 0.210 molar of HC2H3O2. What is the concentration of H3O plus at 25C? So the first thing we should do is write down our KQ expression. H3O plus times C2H3O2 divided by HC2H3O2. Notice H2O is a liquid, so it is not here. Now let's set up our ice table. So initial change equilibrium, our reactants and our products. We put in the initial concentrations as given. And remember, if I don't give you a concentration, assume it's 0. Alright, so we made our ice table. Step 2 should be calculate Q. And so let's do that. Q, well, we have 0 H3O plus initially. We have 0 C2H3O2 initially. And we have 0.210 molar of HC2H3O2. So Q is 0. 0 divided by anything is 0. And so Q is less than K. And so we're going to make products. So we know the signs of X. For a reactant, it's going to be negative X. And it's only going to be 1X because the coefficient here is 1. Plus X and plus X, again, the coefficients are 1. So at equilibrium, all we do is we add our column, so 0.210 minus X, then X and X. Now we can plug our equilibrium concentrations, our equilibrium terms into KQ. We get 1.8 times 10 to the minus 5, that's what we're given for Kc, equals X times X, so X squared, divided by 0.210 minus X. And what I did here in the next step is I just multiplied each side by 2.210 minus X. Then I distributed this 1.8 times 10 to the minus 5 to each term. And I should get 3.8 times 10 to the minus 6 minus 1.8 times 10 to the minus 5 X equals X squared. Now I'm just going to bring X squared over, so everything, or rather I'm going to bring my left side of the equation over to my right side. So we have 0 equals X squared term, X term, and no X term. This is the layout for the quadratic equation. So now we can solve the quadratic equation to determine what X is. Whenever you see something that is X squared plus X plus a constant equals 0, that's when you know you need to use the quadratic equation. To solve for the quadratic equation, you get X equals negative B. B is the coefficient that goes with this X term, plus or minus the square root of B squared minus 4 times A. A is the coefficient with X squared, so here it's 1, times C divided by 2A. Now this plus and minus means you have to solve this equation twice. The first time you solve this equation, you add negative b to your square root term. The second time you solve this equation, you subtract negative b from your square root term. So you'll actually get two answers for x when you do this. And for me, I got negative 0.00196 and 0.00194. And now, the x you want to take is the positive one. The way to logic this out is to look at the equilibrium concentrations. So H3O plus, our equilibrium concentration is X. You can't have a negative concentration. Like, I can't say I have minus negative 2 liters with me. That doesn't make sense. I have to have a positive number. So you take the positive X and you solve for the equilibrium concentration. So 0.210 minus 0.002 is 0.208, and the other two terms are just X. And that's the whole problem. That's how we solve equilibrium concentrations. There is a second way to do it, and that's through the approximation method. So in the previous problem, our equilibrium constant was a very small number, times 10 to the minus 5. And when you're starting with a very small number and your initial concentrations are very big, sometimes we can assume that the change in our concentration is so small we don't even have to calculate it. For example, let's go back to this previous problem. My equilibrium constant was 1.8 times 10 to the minus 5, and my equilibrium was 0.210. Magnitude's bigger than my equilibrium constant. You can see at equilibrium I have 0.208. So my concentration hardly changed at all. So we could have done the approximation method here. But those are the criteria. Very small k in comparison to your starting initial concentration. Right? So let's see how we can use the approximation method in our next problem. So it's just a very general equation here. We have A goes to B plus C. Our K is super tiny, 1.0 times 10 to the minus 5. And we have a large starting amount, 1 molar. So we are roughly 100,000 times, no, 1,000,000 times more starting concentration than our equilibrium concentration. And I'll explain what it means to be valid change should be less than 5%. I'll show you what I mean by that at the end of the problem, but based on what I'm saying there, you can only use the approximation method if this criteria that I'll explain in a minute is met. So let's solve this. Start with KQ. Do our ice table. Initial concentrations. We calculate Q again. Q is 0, so we're going to make products. Therefore, we know the signs of X. We know equilibrium. And we can plug them into our equilibrium concentration. Or our expression, rather. Now, the approximation method is 1 minus X. This X, we're going to assume is going to be small. Small enough that we can just say it is negligible. For example, 1 minus 0.001, that answer is 0.99999. You can just round that up to 1 and say you still have 1 left. That's what we're saying. We are approximating our X will be so tiny, 1 minus X here will still approximately be equal to 1. And we can use that to our advantage when solving this mathematical problem. We can just say this is X squared divided by 1, because we're going to say this minus X is 0. Solve for X, and we get X is 0.0032. And what I was saying about the 5% rule, your X should not be greater than 5% of your initial concentration. So we take 0.0032 divided by 1 times 100. That is 0.32%. So our approximation was valid here. We can make this 1 minus X equals 1 approximation. This number was greater than 5%. We know that approximation was not good, and we would have to use the quadratic equation. All right. So just a couple more things about equilibrium. So when you're at equilibrium, the concentrations will not change once you're at equilibrium. The concentration of the reactions and products will remain the same unless you do something to change that. And by that, it's raise the temperature, change the pressure if you're using gases, add reactant, add product, take away reactant. All those things will disturb equilibrium, and then your reaction will go back to equilibrium. And so when you disturb your system, you'll go back to an equilibrium, but your equilibrium constant will be the same, but the concentrations will be different unless you change temperature. The only way you can change an equilibrium constant is by changing your temperature. So keep that in mind. A change in temperature will mean a change in equilibrium constant. Anything else you do, you may disturb equilibrium, but the equilibrium constant will always be the same number. Alright, that's it for this video. I'll see you in the next video.